Okay, so this video is about the motions of the Earth, and basically the motions that the Earth does are similar and have similar effects as the motions of the other planets and the moons around Earth, or the moon around Earth and the moon around those planets. And so by the end of the day, you got to make sure that you can describe what each of these three motions are and how they affect the Earth. So the three motions are rotation, revolution, and precession. So we start with rotation. That's the spinning of the Earth around its axis. So there is an imaginary axis, a line that runs from the North Pole to the South Pole, and the Earth spins around that. That's like a top, okay? Or someone, spinning on ice skates, or a ballerina spinning. Those are all rotations, okay? The Earth spins counterclockwise, we say relative from the North Pole. So you're looking down at the North Pole, it's spinning counterclockwise. And how long does it take? You already know this. It takes 1 day, 24 hours. So when we look at the Earth, this model of the Earth, we see we're looking down at the North Pole, and the arrows indicating the rotation, the spinning of the Earth, and the axis would be going straight through the Earth right here. Okay, here's North America. Oh, here's us right here. This is the Earth from its side. Again, it's rotating. So there's an imaginary line that runs through the center of the Earth from the North Pole to the South Pole. That's called the axis of rotation. And the Earth is rotating from west to east. And so here we are close to the West Coast. And close to the East Coast. I'm sorry, right here. And this is the West Coast. And this is why we have sunrise happen earlier in the day. Okay. This animation isn't that great. If you want to click on it, feel free. Okay, what does rotation do for us? Well, as we've already seen in class, and like that Stellarium program, it causes all the objects to rise in the east and set in the west. And those celestial objects are things like the sun, the moon, the other planets, and all the stars. That is all that rising in the east and setting in the west is caused by rotation. We also saw that in the northern sky, we have the star Polaris that doesn't appear to move, and the stars around Polaris, which are called circumpolar stars, make circles around Polaris, again, because of Earth's rotation. So the Earth spins at a constant rate. The Earth is circular, and it spins one full circle in a day. And so if we take that 360 degrees that a circle carves out and divide that by 24 hours, we get this rate of spin of 15 degrees every hour. Okay, so the Earth is spinning at a speed of 15 degrees per hour. We talked in class how we're spinning at a speed of, some places, like where we live, 600 miles per hour. Okay, well, this is just a different way to measure that rate of spin. Everywhere on the Earth, you're spinning at 15 degrees per hour. And because that makes objects in the sky look like they're moving, they basically move across the sky 15 degrees every hour. And so in your homework, you'll see some Regents questions that say things like, the sun moves 30 degrees in the sky. How long did that take? Well, if it's 15 degrees every hour and the sun moved 30 degrees, that means that you were watching the sun, recording that for 2 hours. Okay, so the stars move at 15 degrees per hour, and the planets move at 15 degrees per hour. At least they appear to move due to Earth's rotation. Okay. The other thing that rotation does, this last piece here, is it makes things that are moving on the surface get deflected. So just if you were like running on a floor that was spinning, it'd probably knock you on your side. Well, the winds that move over the surface of the Earth and the ocean currents that move over the surface of the Earth get knocked on their side, or they get deflected because they're moving on a spinning Earth. And we have evidence of those things. Okay. So we start with some of these videos. Okay. So here's a video of the sun. Oh, here's some inspirational music. Great. The setting sun, that's caused by the rotation of the Earth. Oh, get ready for this one. No inspirational music. Okay. And imagine, again, this is kind of odd because it looks like the moon is rising, but really it's the Earth that's rotating and it making it look like the moon is rising. Well, okay, that's where the guy sneezed. Check this out. Okay, so this swath, this band is the Milky Way. So we're looking into our galaxy. We're looking into, hundreds of millions of stars. And again, the reason it's appearing to rise in this part of the video is because of the rotation of the Earth. Whoa. We're going to turn that music off. Okay, so these are time-lapse or open exposure photography. And these are things called star trails. And so instead of having the shutter of the camera open and close, they leave the shutter open and record the light from a single dot, a single star, over several hours. And so these are carving out what we call star trails, okay? And if we measured one of these star trails to be, let's say, 15 degrees long, I bet you could tell me how long they left the shutter of that camera open. The other thing we notice is because these star trails are moving in these circular paths, in some of these pictures, just out of view here, we would have one star in the middle that wouldn't be moving. This is pretty cool because this is a really bright star and it's probably not a star. It's probably an object that's bigger than a star that's making a trail over a several hour period. Again, this is caused by the rotation of the Earth, the apparent movement of the stars. All right, so we're done with those videos. You should go out and check those things live sometimes. It's pretty cool. It doesn't happen that fast. Okay, how else do we know that, or how do we know that the Earth is rotating? Well, obviously we have, I think it's obvious, we have pictures from space and videos from space. And we can, the last 40, 50 years, we've been able to see the Earth spin from space. But even for, a couple hundred years, people have known that the Earth is rotating, even though they can't really feel its motion. And one way is by this thing called the Foucault's pendulum, and the other is by the Coriolis effect. So those are when you hear these two terms, okay, what you're going to think is, oh yeah, that's how we know that the Earth rotates, even though we can't feel it. So Foucault's pendulum is just a pendulum. It's like a swing. I have a picture of it in a minute, but it swings back and forth over time. And if you watched it for many hours, it would appear to change direction. And that's evidence that the Earth rotates. The other piece of evidence is the Coriolis effect. And that's kind of like I mentioned before. We can see the effects of the spinning Earth on the winds that move on its surface or the ocean currents that move on its surface, and they have curved paths. That effect is referred to as the Coriolis effect. Both of these pieces of evidence, the name comes from the scientists who basically figured this out. So we start with Foucault's pendulum. This is the Pantheon in France where they have a bunch of dead people buried. And what you see here is in 1851, Jean-Bernard Foucault hung this long string with a heavy mass on the end, and he set this pendulum swinging back and forth. Okay. This basically says what I just said. Okay. And so this is like a time lapse of a current one. You had this heavy bob swinging back and forth. Okay. Here's actually a current picture from that same place. They hung this is a newer pendulum, but this pendulum swings back and forth. And you might say, how does a swinging pendulum prove that the Earth rotates? Okay. Well, we take a look at these videos here. Here's a modern pendulum in a museum. If you can read, I believe that's Spanish. Maybe you could tell us where this museum is. Okay, and so we have a heavy bob swinging back and forth. This is a pendulum. Okay, and what Foucault said is, if this pendulum were swinging on a place that was not spinning, that is a non-spinning Earth, it would just go back and forth in the exact same line or the exact same path. But because the Earth is spinning underneath, the direction of the pendulum changes a little bit over time, very slowly. And so this fancy apparatus is a way to show that happening. And so I'm going to just backtrack here. You're like, oh no, don't go backwards, Mr. Fang. Yes, this thing is going to go back and forth and you see these little pedestals, these like, almost billiard balls set on top. As that pendulum is slowly changing direction, it eventually knocks over a series of these balls. But it's if we watched it in like time lapse. All right, check this out. Okay, here it is in time lapse. It's going back and forth, blah, 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 really, and the direction is slowly changing over time. Okay, but the pendulum's direction is not really changing. What is really changing is the Earth is spinning underneath it. Right? The pendulum isn't really touching the Earth. It's freely it's like connected to the ceiling with like a swivel. So it swings freely. Because the Earth is spinning underneath it, it makes it look like the pendulum is changing direction. Okay, and so this is how we know the evidence for Earth's rotation. Okay, the other piece of evidence is, again, the Coriolis effect. Okay, and that's evidence that shows things moving on Earth's surface get deflected because they're moving on top of Earth's surface. Okay, so in the northern hemisphere, things get deflected to the right, and the southern hemisphere, things get deflected to the left, as you can see in these pictures here. Okay, and so this is a little kind of animation here. Okay, and so I'll do my best to make this big. And so watch this. This is going to show a plane flying from Anchorage, Alaska to Miami. Now the plane is trying to fly straight, but look what happens to its path because the Earth is spinning underneath it. Okay, if it just beelines straight for Miami, it's not going to end up there because during the time of its flight, the Earth spun underneath it. So that's called the Coriolis effect. We can see that. This is pretty cool. I have one of these rotating platforms that students sit on, and they spin and toss this ball back and forth. Okay. Now, before they're moving, they make a nice straight path, passing it back and forth from one nerd to the other nerd. Okay. Now, once they're spinning, they're still throwing it straight, but look what happens to the path of the ball. They are really throwing it straight, but you'll notice that the path of the ball doesn't go straight. The path gets curved. And on top of that, the path doesn't really get curved. What really happens is that the path looks curved because the people underneath it are spinning. And this is referred to as the Coriolis effect. Okay? And I think they draw a picture of this on here. Whoa. Okay, so that curved to the right path is caused because the people underneath are spinning. Okay, Coriolis effect. Great. If you want to watch more of the video, go for it. Okay. Good stuff. Okay, so one way we see that on Earth is with videos of hurricanes from space. So this is a satellite image. Actually, I already had this over here. Okay. And if you watch this hurricane, this is a giant tropical storm. You can see that it has these spiral arms. It looks very much like a galaxy, a spiral galaxy. And the reason it is spinning is because of the rotation of the Earth underneath it produced a spin in this giant storm. Right? And they actually spin in one direction in the northern hemisphere and the opposite direction in the southern hemisphere. Okay? So this is evidence of the Coriolis effect, which is evidence that the Earth is spinning. Okay, here's a video of ocean circulation. All right, a little more complex than what we saw with the hurricane, but what you basically see in the ocean circulation, and what I'll show you in another simpler diagram, is that these ocean currents are largely controlled by the Earth spinning underneath them. In fact, they make these little eddies. Okay, these are these small circular flows that are localized. But when we look at a world map of this this ocean circulation, they make giant, basically circular spinning paths because the Earth is rotating underneath it. And this is referred to as the Coriolis effect. Okay. Feel free to go back and watch more of that later. It's pretty cool. Okay, so on your Earth Science reference tables, this is page 4. And what you see in here, like I've drawn it here, is that we have these ocean circulation patterns, which are giant, basically circular flows. And the reason that they take on that path, I mean, one reason, is they're bound up by the continents, but also due to the spinning or the rotating of the Earth underneath it. Again, Coriolis effect. Okay, we just watched this one. Now, another, a little bit more complex result. This is a diagram from page 14 of the reference table. This is these are wind belts, and so they are also deflected. Okay, these curved paths are deflected due to the rotation of the Earth. Okay. Revolution. So before we get into this, I suggest you pause this video and take a break. Okay, great. Revolution. Okay, rotating with spinning. Revolution is the movement of one celestial body around another. So this is like the Earth orbiting around the sun. We have doors that revolve. You go around that point in the middle. Okay, so the orbit is the name of the path that the Earth follows as it goes around the sun, or really any path that one body is moving along as it goes around another body. So the moon has an orbit, and then Jupiter has an orbit. Okay, so just like the spin was counterclockwise, if we look down at the sun and the Earth is going around or revolving around the sun counterclockwise as well. And you know that this takes 1 year to happen. And so here's kind of a simple diagram of that happening. Here's the sun, here's the Earth in March, and you can see it revolving around the sun. You will also notice that we have an axis of rotation that I described earlier, and that's what we're rotating around. So we're doing both of these motions at the same time. You'll notice that this axis is tilted a little bit, and that's going to be extremely important when we talk about seasons and seasonal temperatures. So, but to reiterate, the Earth revolves around the sun once per year. Okay, how does that motion affect the Earth? Well, like I just said, it causes seasonal effects. That is, we've got different stuff happening in January than we have in June. So one of those differences is the constellations, exactly like we saw in class. In the summer, you see things like the summer triangle. In the winter, you see things like Orion and Gemini. So you have different constellations in different times of the year. Okay. So the revolution, along with the fact that the axis of rotation is tilted 23.5 degrees, like we saw in the diagram, that causes us to have seasonal temperatures, or just that causes us to have, spring, summer, fall, and winter. Okay. So note, this is one of the largest misconceptions in earth science. Many people think that summer is summer and it has warmer temperatures because the Earth is closer to the sun. That is false. The Earth is closer to the sun in December, early January. How can the temperatures be colder if we're closer to the sun? Well, that distance from the sun has no effect on temperature. What has an effect is that tilt. So you'll notice if we go back here, when it's winter and we're a little bit closer, that tilt is away from the sun, and that has effects on the sun's path, which we're going to see in one of our activities here. When we get to June, now that tilt is towards the sun, and so that makes the sun's path change, and the sun is in effect stronger. So even though we're farther away from the sun in June, the fact that the tilt is towards the sun makes the temperatures higher. If you look at the in-between months, like September here, and then March over here, the tilt really isn't towards the sun or away from the sun. And so it's kind of like in between. And that's why we have kind of in between temperatures. So again, to reiterate, the seasons, the seasonal temperatures are caused by the revolution of the Earth around the sun and the fact that we have a tilted axis, tilted away in the winter and tilted towards in the summer. So here is the slow change caused by revolution. So instead of being time lapse for a couple hours, this is time lapse for a year. And so when you get So when you're asked questions about, seasonal effects, try to be specific. Talk about things like the change in what you saw with the leaves, or the change what you saw in the types of precipitation, or the sounds of the animals. Don't just say seasons. Try to be a little bit more specific. Okay, so again, we have seasonal constellations. We talked about this in class. The zodiac constellations kind of go along with the seasons. And remember, even though my season or my constellation for my month is Leo. Okay, so we find that constellation here. The crazy thing is Leo is the constellation or the sign for when you're in August, which would be right here. But if the Earth were in this position, I couldn't look through the sun to see Leo. Okay, what would actually what would have to happen is that I would have to revolve around the sun until I'm in this position, somewhere here between January and May. When the Earth is in this position, then I can see Leo. Let's take another example. Look at the Earth right here in May. When you're on this part of the Earth and you're looking at the sun, it's daytime. When you spin around or when you rotate to this side of the Earth, it's nighttime. So when it's nighttime, I can see these constellations, Scorpio, Libra, and Virgo. I cannot see any of the constellations that are over here because the sun is so bright, it blocks the light from those stars coming back to Earth. When this planet orbits around, 6 months is in this position, it's the exact opposite. I can now see Pisces, Aries, and Taurus, but when the Earth is in this position here, it cannot see Scorpio, Libra, or Virgo. So those are seasonal constellations. These are springtime constellations, and then that would mean these are fall time constellations. Okay, and so that's caused by the revolution of the Earth. Similar graphic. Okay, another term we have to throw in here is called parallelism. And basically what that means is that the Earth axis doesn't actually wiggle back and forth towards and away from the sun. It actually is always parallel to itself in the orbit. And what happens is because we're revolving, its position relative to the sun changes. Because of this, the axis of rotation always points to Polaris, the North Star, and that's what makes it the North Star. That's the reason that it does not move in the sky, and it's the reason those other stars make circles around it. It's the reason it's always in the northern direction, and it's the reason that it tells you what your latitude is on Earth. So if Polaris is 45 degrees in the sky, I know I'm standing at 45 degrees north latitude on Earth. Okay, so you'll notice in this figure, it looks just like the one we had earlier. Here's the axis of rotation. It points away from the sun in December and towards the sun in the summer. But if we look at these 4 axis lines, they're all parallel to each other. If you could compare them, parallel lines like from math class. But if we went very, very far away in this direction where they're pointing to, they would all basically be pointing to the same star. Remember that the star is super far away, but it's also super huge. So even though these lines are not right next to each other on our scale, on the very, very large scale of the galaxy, these were basically a dot in space. Our whole solar system is kind of like a little dot in space, and our axis is pointing to another dot in space. We call that Polaris, and that's the North Star. And here's a figure of that. So our axis of rotation points to Polaris, making it the North Star. Now, this last motion of the Earth, precession, is one you'll never see in the regions, and one that never really affects us day to day or year to year. But it's called precession, and it's actually the wobbling of the axis. So I just told you that the axis basically points to the same spot all the time. Okay, that's true for my lifetime and for your lifetime. But over tens of thousands of years, the axis of rotation actually does wiggle, okay? And so the Earth is spinning, and here's the axis of rotation. And right now it's pointing to Polaris, but over, it's something like a 24,000 year period, it actually carves out a circle. It wobbles on itself. If I will show you in class this demonstration of a gyroscope that does this. Here's a top, a spinning top. A gyroscope is like a spinning top. And this spinning top, the top actually wobbles. But it takes so long that it really doesn't affect you and I in our life. Our North Star will always be the North Star, Polaris. But in thousands of years, the North Star will be a different star. It will be Vega. And that will be the one that doesn't move in the sky. And that will be the one that's always due north. In the time of the ancients, the Egyptians, they had a different North Star. So this is the stuff I just mentioned, okay? That the North Star will change because of precession. Eventually it will be Vega, right? But in the time of the Egyptians, their North Star was Thuban. So a couple thousand years ago, this axis of rotation was actually pointed towards Thuban. And in 13,000 years, it will be pointed at Vega. So humans are here in 13,000 years. Vega will be the North Star. Okay. Now, the other thing that they think it might cause, but this is more complex, are cyclic ice ages. Hopefully you remember what cyclic means. It's a pattern that repeats itself over time. And so rotation is cyclic. We repeat the pattern every 24 hours. Revolution is cyclic. It repeats the pattern every year or 365 days. Precession is also cyclic. It repeats its pattern in something like 20,000 years. I think it's actually 24,000 years. And so that causes us to go in and out of ice ages. So every 24,000 years or so, we're in an ice age. And then we come for thousands of years, we warm up and come out of the ice age. And then for thousands of years, we cool back down and go into an ice age. People, humans have lived during ice ages. But modern humans, the ones you've been studying in global studies and who have civilizations and have settled places, they have all lived since the last ice age effectively ended. So about 15,000 years ago till about 10,000 years ago, all of New York State was covered with ice. And after that, as the ice retreated and basically melted back towards Canada, people started inhabiting what we now call New York. But in thousands of years, that ice, if it follows this same pattern, when we say advance, the Earth will get colder and we'll have another ice age. The Earth will not be covered completely by ice, but basically the ice that's near the North and South Pole, those ice fields will grow and cover larger parts of the world. And so that we have evidence of that, extremely strong evidence of that happening in different cycles for hundreds of thousands of year period. But one of the ice age cycles is a 20,000 year cycle, and it's caused by this precession of the Earth. All right, so to summarize, key ideas from all of this stuff. We have three motions that the Earth does, and they're all cyclic motions. That means that whatever they do, they repeat over and over again. And so the rotation is a 24-hour cycle, and that basically things that happen every 24 hours are probably caused by rotation. Revolution is a yearly cycle. So again, things like seasons or things that happen like once per year or that are in a yearly cycle are probably caused by the revolution of the Earth. And precession is something that is interesting, but really doesn't affect us in our lifetime. All right. If you want to look at the rest of the stuff, it's a bunch of pictures or whatever. but don't feel you need to. This has already gone on long enough. All right, thank you. If you have questions, email me.